If you recall, last week we started talking about flux integrals. Flux integral, we were just writing what looked like a line integral, but instead of C, it says S, and instead of dr, it says dA. So we're changing what we're representing here. So we're still integrating f dot dA, but we're integrating over a surface S. Oh, we're not doing dr anymore. We're doing dA. So we're integrating over a surface S, f dot dA. So F is a vector field, just like normal. We're imagining the vector field of being like fluid or air flowing through the room in three-dimensional space. S is going to be some surface in that three-dimensional space. So like a net catching air particles as it flies through. I don't know. That's physics and engineering. You didn't hire me for that stuff. We just have some hypothetical surface in three-dimensional space and some vectors that are flowing through the surface. And we want to, the framing that we're going to use is we're going to imagine the vector field is a velocity field flowing through the surface. So the vector field is going to say how fast all the particles are going everywhere. And then we're going to watch those particles fly through this surface. And that's going to tell us if we take the area of the surface and multiply that by how fast the particles are going through, we can get the flow through the surface, the volume going through per second, change in volume per second. So this is the flux of flux integrals. How fast the water is going through a pipe times the area, the cross-sectional area of the pipe. That'll tell us how much water is flowing through. If the water is flowing at 5 meters per second through a pipe that is 1 meter square, we'll get 5 cubic meters per second. If we're getting the same 5 meters per second speed of water flowing through a pipe that is 4 square meters, then we have 20 cubic meters per second flowing through that pipe. How fast the water is going times the area of water that's flowing through. That's going to be our base model framing for flux integrals. We always want to have some kind of base model framing, like our line integrals is about work. Work is equal to force dot distance. Our basic one variable function integrals, our simple integrals, represent area under a curve, and so on. Double integrals could be the volume under a surface. Triple integrals are the more complicated version of that. So that's the framing. That's the way we want to think about flux integrals. We're imagining a vector field flowing through a surface. Whatever we need to do to make the vector field flowing through a surface. We could also have an electrical field flowing through. I don't know what electric field flow through. I am too far from when I had the equivalent of physics 260. Bummer that I fixed the mathematical knowledge and I just kind of like let the physics knowledge slide. So I don't know, something had to give, I guess. So in integral notation, this is another important aspect of what we're doing here, being the math class. In integral notation, what we are saying is evaluate the f dot dA. Take this multiplication and evaluate that at all the points on the surface S. That's what this integral notation is about. At all these points on the surface S, make this calculation, then add up the results. Now, this is a really weird kind of adding. This is the kind of adding that we learn in calculus because this is continuous addition. There's no room for a plus sign because we're adding up at all the points on the on a continuous surface. There's nowhere to put a plus sign. We are creating a model for the surface as a bunch of points. And we're giving those bunch of points the same normal vector on some small area. Just like we made our functions constant for small pieces of our interval way back when we first started doing integration. So the big picture here is that we're looking at small pieces and using this constant normal vector for a small area on the surface S. We're thinking of this the surface S as a bunch of little flat areas, and I'm grabbing a normal vector to each of those flat areas. So this is the same kind of integration thinking. So our integration thinking is the same as it always is. We're going to use a discrete model for our the continuous. We're going to use a discrete model of a continuous thing. The surface is going to be a lot of flat areas that have a normal vector. In this case, the surface we're modeling as a bunch of flat areas with just one normal vector. So if we imagine we have this curved surface, trying to be consistent because I want to forward of consistent. This is the game that we always play in calculus. I want to add up a bunch of stuff over a continuum, and I need a mechanism for making addition. I need a place to put the plus signs. So instead of looking at this curved surface where the normal vector is continuously variable, think about a bunch of normal vectors along this surface. The normal vector is continuously variable. So we model that by making the surface flat in sections. So I say, okay, all this curvy bit here, instead of a bunch of normal vectors, I'm going to use this. I'm going to say it's flat right there. That area is dA, and normal vector is perpendicular. So now I look at the vector field at some point on this piece, and find the dot product of the vector field and this vector normal to the surface. I'm just thinking of the surface as a bunch of normal vectors. I shouldn't draw them like from point to point, but. And then we just make smaller normal vectors. We're just creating a model. We're just creating a model for the curved surface because there's a continuously variable normal vector. Our situation is that the normal vectors are continuously variable. So we make things flat. We're modeling the surface with a bunch of flat areas. Our integration thinking, same as the integration thinking always is. Any questions? Is everybody okay? So I'm going to steal an example because I always steal examples. I find a favorite example that I just steal it. Mostly because I get to remind you of something that you may have forgotten. And we'll either pretend that you forgot it or you'll actually remember it. or you'll never have seen it before and we'll just pretend that you remember it, which is really how we remember things anyway. You know what I mean? You don't recall the events. You just recall the last time you recalled the event. And that event may never have happened. Do you know what I mean? Like like memory and perception are really weird things. We don't actually see anything. Our eyes take in information and our brain processes what we just saw. And a lot of times, if we're not paying attention and we have to go back into our memory, our brain will make shit up that we definitely are convinced that we saw. Pass a lie detector test, we saw that happen and it didn't have to happen. It might not have happened. What I'm telling you is that there are things that you remember and you might remember them and believe them very strongly that never happened. And we have no way of knowing. You cannot internally decipher which one of those things are real. Do you know what I mean? I have a very strong memory that I'm pretty convinced, I'm pretty sure it is not true, but I can picture it. And if I took a lie detector test, I would pass that I remember it. It concerns The Gambler, the song, and Kenny Rogers being on The Muppet Show. I don't know if you know who Kenny Rogers is. I don't even know if you know what The Muppet Show is. But The Muppet Show is a variety show with puppets. So look up The Muppet Show. Like Sesame Street, Muppet Show, same kind of thing. Anyway, so they would have celebrity guests. It was like Saturday Night Live with puppets for kids. And so they would have musical guests. And then the musical guests would do skits. It was like a whole thing. But anyway, there's a song that Kenny Rogers did called The Gambler, came out in 1978. November 15, 1978. I don't know why I know that. I don't know why. I just do. But in the song, it's about Kenny Rogers meeting a gambler, and the gambler gives him some advice. And after the gambler dispenses the advice, the gambler falls asleep and dies on the train. When I first heard the song, I, of course, liked the song because it was 1978 and it was a popular song. And I'm like, oh, wow, this is what people do. We like popular songs. So, yeah, this song is cool. I like it. I still do. Who knows why? But I didn't know the context of the song until Kenny Rogers shows up on The Muppet Show and they have Kenny Rogers sitting in a train with a bunch of Muppets and one, like an old man Muppets. There's like 3 other old man Muppets. I just called Kenny Rogers an old man Muppet. There were 3 old man Muppets and Kenny Rogers sitting on a train. And one of the Muppets is the gambler. I'm like, oh, this is awesome. I'm going to watch a story version of this song that I really like, not realizing I don't understand the song. Then they get to the part, and somewhere in the darkness, the gambler, he broke even. And at that point, like a ghostly image of the gambler just kind of like puppet falls asleep. Then a ghostly image stands up. And that's when I realized what he meant. He meant the gambler died. When he said final words, it wasn't final words because that's the last thing he said to me. It was final words. That's the last thing he said. Gambler is dead now. That's what you meant by broke even. And I have this distinct memory of sitting in my stupid living room in Moss Beach, California, on California Avenue, 363. Don't go to the house. I haven't lived there in years. Sitting in the living room, looking at that big wood grain TV in the corner, because there were gigantic boxes back then, and realizing that dude dies in this song. This song that I've been singing for a year has been about a dude saying, hey, this is what you should do, and then dying. I don't even know if that's true. I know that's what the song's about. I know I watched that episode of The Muppet Show because I watched all the episodes of The Muppet Show, but is that really when I realized the song was about the dude dying? Because it is now, but it might not have been. Do you know what I mean? Your memory might be a lie, is what I'm saying. What are we talking about? This is why I like math. Because math will not fuck with you in that way. You can fucking count on this shit. See? Integration thinking? Same thinking. Integration notation? Same thinking. It's all the same stuff. Calc 3 is the coolest calculus. And one of the reasons that Calc 3 is the coolest calculus, one of the reasons that Calc 3 is the coolest calculus is that we've gotten kind of the integration and derivative thinking out of the way, and we're starting to do more stuff with it. We're starting to do more stuff with it. It's like when you first learn an instrument, you learn how to play the notes and how to hold it, and you learn how to use the proper techniques of doing all the things, but you don't really start by playing songs. I mean, unless you play guitar, because everybody learns to play guitar by just like picking it up and trying to play a song and doing it badly. But when you go for the instruction in the instrument, they say, this is how you're supposed to sit. This is how you hold your hands. This is where you put your fingers on the thing. Like when you learn, I have also not learned a lot of martial arts, but like in learning a martial art, you don't just start fighting people. You just don't start fighting dudes. You learn how to stand, you learn how to move, you learn how to defend, you learn how to strike. Those are the categories that I can think of because I'm learning lightsaber fighting. I don't want to learn a real martial art. I don't want to learn something like it might be practical. I want to learn how to fight with lightsabers in a fake environment. So you learn those things, and you got to learn that before you start fighting people, especially if you're going to be hitting people with plastic sticks. You don't want to hurt them. I mean, you want to simulate hurting them, but you don't want to actually hurt them. You know what I mean? And so Calc 1 and Calc 2 are Daniel-san and Miyagi, where Daniel-san's on the boat. He's like, well, when am I going to learn to punch? When you can learn to stay dry, right? And we've learned to stay dry at this point, and we can actually now start doing shit. We can take our integration thinking and our integration notation and apply it to something different, something new. That's the point. Learning like calculating a few flux integrals, that doesn't mean shit. Learning what the notation is, learning what you can do with the thing, and learning how you will express that thing in notation, so that when you come across something in your future classes where they say, we calculate this with a dot product, you can immediately think, if we're calculating something with the dot product, can those factors be continuously variable? If so, this is a calculus problem. That's it. That's the point. That makes sense? So you are correct. Calc 3 is the coolest calculus because we have learned to stay dry. We have learned to stay dry. And now we can start sparring a little bit. Anyway, what were we talking about? So this is the reason I like this problem. I don't know when I first started stealing this problem. At least I'll admit that I'm stealing it, right? So I know that the water is flowing through the pipe at a constant 5 centimeters per second. We're going to ignore friction. And it's going to be 5 centimeters per second through the pipe everywhere in the pipe. Right up against the edge and right down the middle. So like, I don't think I like that. Then just make the pipe bigger, and then the difference will be a lot smaller. I don't know. When was the last time I put fluid dynamics? But with this information, if water is flowing through the pipe at 5 centimeters per second, and the area of the pipe is 4 pi square centimeters, then the volume of water, the flux through the pipe, the flow through the pipe is 20 pi cubic centimeters per second. So here our flow is just the 5 centimeters per second times the 4 pi square centimeters. There's our flow through the pipe. Flux. here's the thing. The area is not always 4 pi square centimeters. It's 4 pi square centimeters if I draw a circle perpendicular, if I draw a circle as the cross section of the pipe. What if I draw an ellipse? If I just take this circle and tilt it at an angle, let's say theta with the flow, I'm going to show some awareness of my situation and not say what I was about to say. This is going to be a larger area. That's going to be an ellipse. Over here, we had a circle. But over here, we have an ellipse. The area is going to be larger. The area is going to be larger. So the water is flowing through. But we are at an angle. I got distracted by story time, so I'm going to draw the angle. So the area is larger, but so the area is larger. So the area, if this is at an angle of theta, the area is 4 pi. As you recall, so I'm stating that you all remember this. You've seen this before. So pretend that you remember that you saw this before, right? Everybody remembers the angle of an ellipse. We're just going to take a circle and put it at an angle. We just need to divide by the cosine of the angle at which the ellipse sits, right? Of course, right? See, all you have to do is nod. And you're like, oh, yes, of course. And put the of course face on. And the degree to which you put your of course face on is the degree to which you don't actually remember this. So I can read that. I can do the calculations. It changes continuously, but I can tell. We just divide by the cosine of the angle that we put the ellipse at. This makes it larger, right? So if theta is 0 degree, if theta is 0 degrees, then cosine of theta is 1. And so we just get 4 pi. But when theta is 90 degrees, then our area is undefined. Because I've taken my circle, here's 0 degrees, and I start increasing the angle that we're making. But I can't make theta equal 90 degrees because that would be like parallel. And that makes sense because 4 pi divided by a cosine of 90 is 4 pi divided by 0. And that would be like an infinite area. We could interpret that one as like infinite area. We wouldn't want to say that the area is infinite because that wouldn't make any sense. It's definitely undefined, but oops. Trying to write square centimeter. So the area is larger, but the amount of flow, we're not worried about the amount of flow. We're not getting all of the 5 centimeters per second. We want to know the flow normal to the surface. I want the dot product of the flow through the surface. So I don't want 5 centimeters per second. We're at an angle of, so even though our area is 4 pi, over cosine theta, the flow that's going through the pipe is not all of the 5 because it's coming through at an angle. Before, when it was perpendicular, we were getting all of it. We're not getting all of it now. We're getting 5 times the cosine of theta. And that's our flow. So we still get 5 cosine of theta times 4 pi over cosine theta. The cosine thetas cancel out. It's still going to be 20 pi cubic centimeters per second. How much of the flow is normal? Any questions? So we've talked now about the framing. Imagine the vector field is a velocity field flowing through a surface. We've talked about the notation of a flux integral. The vector field is flowing through the surface S, and we're finding the dot product. I want the vector field dot a vector normal to the surface. And I want to calculate this at all the points because we've also talked about the integration notation. We've also talked about integration thinking and how it applies in this flux integral in the same way we talked about integration thinking in line integrals. Any questions? We still can't really stay dry yet. So we might not, once we finish calculus, multivariable calculus, then we can get into some sparring. But it's still going to be light contact because I don't want people to get hurt. Any questions, comments, snide remarks? If this explanation down here feels incomplete, it only feels incomplete because it was incomplete. I glossed over something, and I waved my hands at it because you need to have to think about it. If I explain it right now and it perfectly makes sense, then you won't think about it later. But I want you to be bothered by this. If you're like, well, I'm kind of bothered by this, I'll see you tomorrow. That's it for today. Have a good day, and thanks for playing.